Hello Year 11 and welcome to our first video here for our 9th topic. We're looking at probability distributions this time, and in this exercise we're going to look at the language around these things, and that's certainly going to be one of the bigger challenges for this chapter. It's not a huge chapter, but we've got to get our head around some different language, and in particular when we use different words to describe the same thing. We're going to see that happen a few times. So, here we go. A probability distribution describes what outcomes can occur and how likely they are. So it looks at all of the outcomes, or in fact we're going to call them values from now on. It's going to look at all of the values, there's the first switch here in language, the values of some experiment, game of chance, something like that. It's going to look at all of them, right, and see how they are spread out, right? So, here's an example. The bag contains 3 red balls, 4 yellow balls, and 5 green balls. One of these balls is chosen at random. And the probability distribution for this can be represented in a table. We're going to call the table the probability distribution. And this is it. So, the values that can take on, right, that the result, if we like, of that experiment can take on are red, yellow, or green. These are not uniformly distributed. They do not all have the same probability. The probability of red would be, well, 3 out of a total of 12, or a quarter. Yellow is a third, and green is 5/12. Now, it's important to recognise here that because this is listing all of the possible values, the sum of the probabilities will be 0. Okay, so these probabilities here will always add up to 0 for a probability distribution. That's an important thing to remember. That'll help us solve some problems. Moving along now. When this experiment is conducted, those values that can result, red, yellow, or green. Now, when we say the collection of those results, what they could be, right, they're going to be our values. But what it is, an individual result. We want to make a fine distinction here between what could happen and what does happen. And what does happen I'm going to refer to as the random variable, and that's normally an uppercase X. Right? It's going to be our random variable. That's what has happened. That was the result of the experiment. The values are what the result could be, but the random variable is what the result is. We write it like this. This is the notation we use. The probability that our random variable is yellow is equal to 1/3. Right? That's what we got previously. Now, in that example there with the coloured balls, the values, right, remember they were the 3 colours, the values, well, because their names are not numbers, that's categorical data. Right? And we're very limited with what sort of calculations we can do with categorical data. And so we won't look at categorical data much anymore. That was just a sort of introductory example. Mostly we're going to be looking at situations where the values, what we've previously called outcomes, take some numeric value. It will be numerical data. Okay. Now, there is another distinction here between numerical values that I can list and numerical values that I can't. You might think, well, I could list all numerical values, but if I said start writing all of the numbers between 1 and 2, right, all decimals between 1 and 2, well, you can start with 1, that's fine. What's the next number after that? Well, you know, there are an infinite number of real numbers between 1 and 2, and I just really can't find the next one. I can't find a consecutive value. Now, if I say list all of the positive integers, there's an infinite number of those, but I can list them in order, right? I can put consecutive values down, 1, then 2, then 3, and so on. I can't tell you what the last one is, but I can always tell you what the next one is. Now, the difference between those things is whether it is discrete or continuous. If I can find consecutive values, if I can list consecutive values, it's going to be discrete. If I can't, it's going to be continuous. Typically, we define these things, or we often explain these things, maybe not define, that discrete data is counted and continuous data is measured. So, another little bit of language here. If there's only one possible outcome of our experiment, that's called a deterministic experiment, and it's really not very interesting, right? The probability of that single value outcome will be 1, right? Not much happens. Now, if all our values have an equal probability, like when we roll a die, right? That's a uniform probability distribution. Uniform, all the same, right? All of the probabilities for each of the values are the same. Here we go, into our first example. 3 coins are thrown. We need to create a probability distribution table, as we looked at before, for the number of heads, right, and graph the distribution. So, if I throw 3 coins, I could have 0 heads, 1 head, 2, or 3. So there are 4 possible values there. But it's not a uniform distribution because, right, now we list the probability of getting no heads out of 3 flips. Will it be 1/2 times 1/2 times 1/2, harking back to our previous topic there, and that would be 1/8. Now, for 1 head, could be the first one, could be the second one, could be the third one, you might want to draw a tree diagram perhaps, to examine the probability of that occurring. But you would find that the probability of that occurring is 3 in 8. Equally, for 2 heads, and then for all 3 heads will be 1/8 again. Remember, we can add these probabilities up, and we should get 1. And we do in this case here. So that's a good check that we haven't made a mistake with calculating one of the probabilities. Here's another example. Maurice flips a coin and counts the number of flips until it lands on heads. On a probability distribution for this experiment. Well, how many values could we have? How many times will Maurice have to flip the coin before it lands on heads? Well, maybe just once, so that would be our first value. Maybe twice. There's a 1 in 4 chance that it would take 2 flips before it lands on heads. Or, yeah, and a 1 in 8 on the third, and so on. Now, can we see the probability of tails, tails, so let's say tails, 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 then heads, so 3 tails and a head, it's 1 in 16. We can see a pattern developing here that we have an infinite number of values. I'm going to use this pronumeral n to represent some number, and the probability of that value will be 1 over 2 to the power of n. So that's a case where we have discrete values, but an infinite number of them. So that's it. That's the language covered off for this first exercise. Categorical data is named data, like red, yellow, blue, Australia, Brazil, and Afghanistan. Numerical data are numbers, right? 1, 2, 3, 4, 5, $6.50, $7.25, right? They're numbers. The result of an experiment we refer to as the random variable and represent it with capital X. The possible result of an experiment, right? Those possible results, not what happened, but what could be, are values, and we use a lowercase x for those. Tricky. Come together as we do more examples. And the sum of the probabilities of a distribution will always be equal to 1. Righto. That's it for the first exercise. Some of those things might be less than clear. I do apologise for that. It is a bit tricky, but as we work through the examples, I think we find that it might be hard to understand why we use so many different words and different naming conventions for these things, but the calculations and even interpreting the questions, not too bad in this instance. Okay. Well, our next video will be expected value, and I'll see you then.